ba 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 director. Man, what am I doing? Hello, and welcome back to the next part in our exciting kinematic series here on Mr. Bell Physics. This is part 4 of our kinematic series, where today we're going to be dealing with projectile motion. Now, projectile motion is a lot like regular motion in the sense that the kinematic equations still apply. However, now, rather than just having an object move forward and backwards or up and down, we have something that is moving both forward or backwards and up and down. Meaning that the scenarios are going to get a little bit more complex and the math is a little bit more involved. But the actual physics of what's going on is still identical to before. So, here we have a practice problem for this. And fun fact for those of you who are watching this on January 12th or 13th of 2026, this is actually going to be your bonus problem if you are in my academic E-block physics class for extra credit, for 10 points of it. So if you are doing your due diligence and watching the videos, studying up, all that good stuff, good on you. If not, then this message isn't going to be too helpful for you. But here's hoping that you guys took the time to take a look at the video. But if you read the actual problem, it reads, a motorcycle stunt driver is going to drive off of a 90-meter tall cliff for an upcoming movie. How long will the cameraman have to film them in the air for? And how far from the base of the cliff will the production crew have to place a crash mat to ensure the driver lands safely? Now, that's a whole lot of words. And that is a 5-line sentence. Jesus. Okay. My mom was an English major. She was an English teacher. God bless her. I can never do what she did for a living. Okay. That much reading makes my brain hurt. So, what can I do with this? Well, like the last episode where we talked about cars and stuff like that, I don't particularly care about the pomp and circumstance of the actual problem. I care about the numbers and I care about the physics. So really, when I'm reading this problem, I don't care that it's a motorcycle stunt driver. I don't care if it's for an upcoming movie. I don't care about, cameraman or how much film or anything like that, or that it's a production crew and that they're using a crash mat. I don't care about all that, okay? What I need to be able to do is interpret this situation back into physics, which means I'm hunting down for numbers and I'm hunting down for values that I'm looking for. Now, the only part that's going to be different here compared to what we are already used to is that now we're both working the X and Y dimension. Now, I understand that at this point in time, before the midterm, I did not make a video for free fall problems or anything like that. Okay, I'm hoping that the 1D kinematics problems will be enough for that. That being said, in the future, I will hopefully make that video. For us here, though, we have movement in the X direction and movement in the Y direction. The kinematic equations, as lovely as they are, can only work in either the X or Y direction, never both. So because of that, we need to take our problem and we need to understand which values are X values and which values are Y values. In order to do that, I like making a table like this. Notice I still have all the same variables that I would normally have. VI, VF, A, T, and X. Okay? They're all still there. They all still mean the same things. Initial velocity, final velocity, acceleration, time, and displacement. But now I need to recognize I'm going to have different values for each dimension here. All right? So, how can I start kind of going about filling in the list here? Well, let's start off by reading off the actual problem, reading off exactly what is being said. Okay? Motorcycle stunt driver is going to drive off of a 90-meter tall cliff. Stop. 90-meter tall. Okay? So here, I'm going to actually color code this. Anything in red is going to be the y-axis. Anything in X is going to be the blue axis. So I'm going to just underline this in red and underline this in blue. That way we have that distinction. 90-meter tall cliff. The word tall in that gives it away that I'm talking about height. Okay? Meters tells me this is definitely a displacement. It's a distance. So displacement in the displacement for height would be displacement in the y direction. So therefore, I know for a fact that that 90 belongs right down here in my table. So it belongs right there, okay, right at the bottom. I know for a fact that that's what they have already given me. Now, I actually did forget a line here. It's not just driving off of the 90-meter cliff. It is actually driving off of that cliff at a speed of 30 meters per second. So I'm going to put that in here. .30 meters per second. Oops, my bad. Okay, bear with me. This is the third video I've recorded today. This is after school at this point. Okay, I haven't had a big lunch. I'm tired, quite frankly, but we're gonna get through it. So we're going at a speed of 30 meters per second. I have to think logically. Okay, if I'm driving at 30 meters per second, does that mean that I'm going up, down, forwards, or backwards? To me, when I'm driving at that speed, I'm going forwards. Okay. Now, if I'm going forwards, that means that I'm working in the horizontal plane, not vertical, horizontal. And if I'm working in the horizontal plane, that means that has to be an x value. Now, meters per second, I know for a fact that is a velocity. The question is it my initial or final? I can figure out it's my initial because I haven't jumped off the cliff yet. So when I jump off the cliff, that is the speed that I am going at. So you put in 30 right there. How long will the cameraman have to film them in the air for? So time is unknown. Okay, how long is going to be a time question. So I don't know time. And how far from the base of the cliff will the production crew have to place a crash mat to ensure that the driver lands safely? They're asking me how far is this driver going to fly, which means I do not know my displacement in the horizontal or x direction. Even then, though, quite a bit of information here is still unknown. Okay, quite a bit of this table is still empty. And that's because with projectile motion, there are a few assumptions that we have to be ready to make. So, what we're going to do now is I'm actually going to take you guys to the back of the classroom so that we can show off some demonstrations to help make this make a little bit more sense. So, join me back there. Hi, welcome back. So, with all of those blank spots on the table, most of what we need is in the x direction. So I want to start off with a demonstration that will help us uncover a little bit of what's going on in the x direction. And what I'm going to use is I'm going to use my good friend Bobbert, the projectile launcher over here. Now, Bobbert is an expert in his field. Okay? As you can tell, he has some pretty nifty headwear here that I gave him for Christmas. And what he is a projectile launching cart. Basically, you push him forward at a constant velocity. A ball, which is in here, will launch upward, and then as he drives forward, something will happen to the ball. So, to show that off, we're going to take our cart here. We're going to make sure that our fire mechanism is cocked. We're going to pull back the hammer. And make sure that our magnetic stopper is there to hold it in place. And then again, all I'm going to do here is I'm just going to push this forward at a constant speed, and then eventually something will happen to the ball. So let's see what happens. So, what happens there is that the ball got fired directly up into the air, meaning that all the horizontal velocity that I had was from the cart already moving. And what happened is that it landed right back in the cart. Now, the reason why this happened is because nothing caused the ball to accelerate in the horizontal direction in either direction. Nothing caused it to speed up or to slow down while it was moving through the air. Now, this also tells us something rather important. Okay, number one, it tells us that our acceleration in the x direction, in theory, should be 0. Okay, that projectile was launched into the air. Okay, and once it's launched into the air, there's nothing acting upon it unless we're accounting for air resistance, which in this case we are not doing. Okay, air resistance gets way too complicated way too quickly. So instead, nothing is acting on it. And because nothing is acting on it, nothing is causing a change in motion or an acceleration. So therefore, we could assume acceleration in the x direction is a big fat 0, big fat goose egg. And because of that, we can also assume whatever my initial velocity in the x direction is also going to be my final velocity, because acceleration is our change in velocity. If that's 0, there's no change in velocity, then therefore, there's no change in velocity. Okay, it starts at 30, it ends at 30. Plain and simple. What this also tells us, though, is that it proves that us doing our math separate for the kinematic stuff is accurate. If vertical velocity had an impact on horizontal velocity, we would have seen it in this demonstration. But this shows us that our vertical components, our up and down components, and our horizontal components, our side to side components, are acting completely independently of each other. Okay? That has happened to happen at the exact same time. See, multiple things can be happening to an object at once. That's why projectile motion can be a little bit tricky sometimes. But overall, all that's really happening here are just two separate kinematics problems. One going sideways and one going up and down. So now I have one more demonstration to show you over on the other side of the room. So, I'm over here now. Whoa! Whoa! Okay, so on the note of our x and y motion being independent, just to prove that without a shadow of a doubt, what I have here is a device that will both launch a ball horizontally that way and will drop a ball vertically this way. Now, when a ball is launched horizontally, not only will it move forward, but gravity will pull it down, right? So this is kind of a device that tests the age-old question of, if I fired a projectile from, say, a firearm, right, bang, and I dropped an object from the exact same height and at the exact same time as when I, bang, fired my firearm, which one would hit the ground first? A lot of people are tempted to say, oh, well, it must be the one that's dropped, because surely, because it's being pushed outwards, our y motion is being affected by that. It's being stretched out. But in actuality, what we find out is that they both fall at the exact same time. So I'll do that again. Okay, if you didn't catch that, make sure you listen for the actual sound of the impacts themselves. Okay, if you listen for the sound of the impacts, if you hear two distinct impacts from the initial hit of those balls, then you know that one dropped faster. But if they both hit at the exact same time, then you know that our y motion, regardless of what our x motion is doing, is going to be identical and is going to be completely independent. So let's see if that works. In 3, 2, 1. They both hit at identical times. So again, what that proves is that our x and y motion act completely independently of each other. Now, we know that the thing causing these things to fall is gravity. And here on Earth, the average acceleration due to gravity is a known value. It's 9.8 meters per second squared. Now, normally, we treat it as a negative value because it pulls me down, right? I try to jump up, and it pulls me directly back down. But when it comes to acceleration, we need to think about what is it actually doing to my velocity. Is it slowing me down or is it speeding me up? When I jump up, it's slowing me down. It eventually causes me to stop rising, and that's caused me to start falling. But while I'm falling, gravity causes me to speed up, meaning that our acceleration, our change in velocity, should be positive. So what we're going to do now is we're going to go back over to the whiteboard over there, and we're going to fill in the rest of the table with what our new assumptions are now, and we're going to see what we can solve. The only other thing that I want to point out is, let's say I take an object, for example, this tissue box, and I drop it, like so. The exact instant that it begins to fall, or that I let go of it rather, it's not falling yet. See, gravity, like any acceleration, takes time to come into effect. Okay? Acceleration only changes an object's velocity if it has time to do so. So therefore, if we weren't moving in the y direction initially, which we're not right now, if I ran off a cliff right now, I'd just be running in the x direction, right? Because I'm only moving forward or backwards. I have no y velocity yet. No, it's not until after I've already gotten off of the cliff and I'm falling, and after some time has passed, that gravity takes a hold of me, starts to pull me down, and therefore my velocity starts to change. So the last thing that we can assume is that our initial velocity in the y direction is a big fat goose egg. So let's head back right over there, fill in the rest of our table, and see how much easier this is going to be to solve now. Diddly-doo, diddly-doo, diddly-doo. Welcome back to the whiteboard. So what I've done here is I've erased the actual problem because all of our information that we got from the problem is already back here on the table. What I'm going to do now, though, is we're going to plug in the rest of the information that we've learned due to our assumptions. So let's start off with the x values. I may not know time and I may not know displacement yet, but I do in fact know acceleration has to be 0. And because acceleration is 0, my velocity is not going to change, which means that therefore it has to be 30. Additionally, in the y direction, I do not have enough information to solve for VF right now. I don't. But what I do know is that my initial velocity is going to be 0 because it takes time for gravity to act upon me. And I know my acceleration is going to be 9.8, the acceleration due to gravity. I also know in this case it's going to be positive 9.8 because I'm falling. Okay, I'm not rising and then falling. I'm just falling. Okay. See the next part in our series, talk about when we have a rise and a fall. Now from here, there's only one piece of the puzzle that I don't know yet and that the question isn't asking for yet. And that would be V final in the y direction. So let's look through this problem and see what we can do. Now time in kinematics is dimensionless, meaning that it does not have an x or y direction. Instead, if you solve for it on one side, you can carry it directly over to the other side. So my goal right now is to solve for t. And if I can solve for t, my life is going to be made a lot easier. Now, your initial reaction may be to say, well, okay, let me look at the x direction first, okay? Because that's what I'm trying to solve for t, and if I have t over here, I also have t over here, but I also need to solve for x over here. So there's more I need to solve for in the x direction. Let's see what I can do with that. Okay, fair enough. Let's take a look at our equations. V final, we know that, equals V initial, we know that, plus acceleration 0 times t. That means that t gets canceled out. We cannot solve for t that way. Equation 2 doesn't even have time in it, so we can't really use that. And we can't even use it to solve for distance because, again, a is 0. So this entire term that has our delta x in it goes away. Okay, how about down here? Equation 3. Well, it has both delta x and t in it, and I don't know either of those yet. When I'm solving an equation like this, there can only be one unknown. Otherwise, it's going to be impossible for me to solve right now. So I can't use that. Okay. And then same thing with equation number 4. Okay, I have delta x over here and I have t over here. I need to know one of those before I can solve for the other. So that kind of sucks, right? So x is off the table. Let's use y instead. Okay, surely, y has something that we can use here. Well, in y, we have vi, we have a, and we have x. 1 has vf in it, so we can't use that. 2 has vf in it, so we can't use that. 3, technically speaking, we could use to solve for t. However, we would be stuck using a quadratic if we did that, which would be a massive pain in the butt. So let's see if there's an easier way to do that. And then 4 has both vf and t in it. We can only use one unknown. So it seems like we're kind of at a bit of a roadblock here. See, this is where we use what we learned last time, where we can use any equation we want so long as we have the stuff for it. So we could actually take care of this missing piece of the puzzle here, this vf in the y direction, to solve the rest of this. See, while we don't have enough information to solve for t in the y direction right now, we do have enough information to solve for vf. See, using equation 2, vf squared equals vi squared, I know that's 0, plus 2, number 2, times a, 9.8, times distance, 90. I have enough information to solve there. Once I have enough information here, I can very easily use, say, like equation 1 to solve for t, carry that back over to x, and then solve for my horizontal displacement. And then I'll be all done. So let's go ahead and do that. So, writing in red because we are doing stuff in the y direction right now, we're going to use equation 2 to solve for vfy. So, v final y squared equals vi y squared, which is 0. So 0 squared plus 2, the number 2, times a, 9.8, times x, 90. 0 squared is just going to be 0, so that we can get rid of. Then in our calculator, we could do out this math to see what we end up getting. 2 times 9.8 times 90 comes out to be 1,764 exactly. So vfy squared equals 1764. Now from here, you may be tempted to say that we're done. Okay, after all, we have vf by itself, right? Not quite so. See, we have vf squared by itself right now. We do not have vf. We need to undo that square in order to finish this out. So let's do that. In order to do that, we take the square root of both sides. Doing that, vfy comes out to be a pretty reasonable 42 meters per second. Now, some important notes on this. The big one being, we are ignoring air resistance. Okay, this number will change based off of air resistance. Terminal velocity is a thing. Drag is a thing. But we are ignoring air resistance to make our lives easier. This still gives us a pretty good gist of what's happening. Air resistance does play an effect on these things, especially on windy days and stuff like that. But for our purposes, they're close enough. So, VF, I'm going to take off the question mark and make that 42. Now I have plenty of information to solve for T. Okay, let's go ahead and use equation 1 to do that. Okay, now that I solve it at 42, I can just reuse that to solve for everything else. So, right down here, 42 equals, that's our VF, okay? VI, 0, plus acceleration, again, 9.8, times T, 0 is just going to do nothing, so that can just go away. Which leaves me with 42 equals 9.8 t. Now, I want to get t by itself right now. And 9.8 is multiplying it. In order to undo something in math, I have to do the opposite of it. The opposite of multiplication, division. So I divide both sides by 9.8. And I get that t is equal to, if I do it in my calculator, I'm getting roughly 4.3 seconds. All of a sudden, this whole problem is kind of opened up. Okay, all of a sudden, I know t. It's 4.3. And because I know it there, I also know it right over here. Now, if I took a look at my x values again, all of a sudden, I have 4 out of my 5 values solved for already. So I just need to find something where I'm solving for t that doesn't have a, because a is 0, and that's going to mess my plans up a little bit. Again, I could use equation 3, but it kind of defeats the purpose to use equation 3 at this point. Actually, no, I could just use equation 3 because I know time. If I didn't know time, it would kind of defeat the purpose of doing this whole thing, right? Because it would mean I had to do the quadratic formula again. But in this case, I can use equation 3. Let's see, what else can I use? I cannot use equation 2 because acceleration is 0, so I get rid of that term. But I could also use equation 4. And you know what? Let's use equation 4 because I actually haven't used it in any of these episodes yet, and I don't use the next episode either. So let's do it now. Why not? So just continue right over here, now in blue because we are in the x direction. Delta x equals 1/2 velocity initial, 30, plus velocity final, also 30, times time, which is 4.3. So let's do this together. 30 plus 30 is 60. Divided by 2, or times 1/2, is right back to 30. So I'm essentially left with here is delta x equals 30 times 4.3. Now, when I do that math out on my calculator, I get a final answer of 128.57 meters. Put it in my box. And at this point, I know for a fact that I'm definitely done because my entire table is filled out. Okay, there is literally nothing else for me to solve here. I have done everything. So, at this point, I can take a step back and appreciate all the work that I just did. Okay, I basically had to do 3 kinematics problems back to back to back in order to actually solve this out. But none of the math was really that bad. It was all about just trying to figure out what the best strategy was. Okay, what the best use of my time and energy was. And hopefully that's a strategy that you can take forward with you when you're trying to solve these problems in the future. So again, if you are in my E-Block physics class and you're watching this before we take our midterm, so basically pretty much right when this gets uploaded, congratulations. You just saw the teacher solve the entire bonus problem for you on the exam, and that's worth 10 points of extra credit on your exam. Big deal. Okay? Hopefully someone takes advantage of it, because I'll be kind of depressed if you guys don't. But if not, hopefully this gives you a pretty good indication of what to do with a kinematics problem. Next episode, we talk about a projectile motion launch when we don't have just a flat horizontal angle. In fact, when we tilt it up a little bit, right? And go at an angle. So until then, thank you so much for watching. Make sure you absolutely smash that like button. Make sure you hit that subscribe button. Ring the bell for notifications so that you know whenever Mr. Bell uploads a brand new physics video. Who knows? Maybe I'll give you the extra credit problem on your test next. Maybe you're lucky. Until next time, thank you so much for watching, and I will, as always, catch you in the next video.